So, we were talking about some reasons why anodic sites can form on the same steel surface, and corrosion can actually initiate without there being a electrochemically different metal or different piece of steel in the vicinity of the corroding steel. So, there are several reasons that we discussed yesterday, primarily dealing with variances on the steel surface due to composition, due to the residual strains or stresses that may be present, and sometimes when you have changes in the cleanliness of the rebar. By the way, I do not know how many of you noticed when you walk up the stairs here, they are working with rebar which is looking spotlessly clean. Yeah, it's a spotless rebar. It's totally clean. Probably it's just freshly arrived from the factory and they are using it for the construction. So that's very good. That's good quality control. But in many sites you don't see that. You see that rebar is lying around in the open for days without being used, and because of that it develops a mill scale on top, right? And that scale is usually a problem, not really a good thing. Now, obviously when rebar gets converted to its oxide or hydroxide forms, there is a change in volume that is associated with that process. So, when iron changes to iron oxide, there is a slight increase in volume, but the hydroxides are the ones which are having a very large volume as compared to the original steel. So, when you have an increase in volume of the rust because of different forms of hydroxide and oxide that forms, obviously there will be a expansive pressure on the surrounding concrete, and this expansive pressure is of the order that it can easily exceed the tensile stress of the concrete, and that causes cracking in the concrete. So, in most cases the concrete surrounding the rebar tends to crack at very late stages of the rebar corrosion. When you have substantial amount of rust products forming, you can have expansions because the volume increases approximately 6 times. So, volume increase when steel converts to its oxide and hydroxide forms is nearly 6 times. I mean the peak hydroxide is 6 times as voluminous as the original steel. Now, because of this there is expansive pressure, concrete cracks around it, and the cracking and further deterioration of the concrete around the steel further increases the rate of penetration of your chlorides or other aggressive agents that are coming from the external environment. So, obviously this will lead to a further acceleration of the attack. Attack will happen faster and faster once the concrete is cracked and the chlorides are able to get in much easier. Now, mainly we deal with 2 different types of corrosions with respect to the mechanism of the corrosion itself. One is arising due to carbonation. And we talked about this earlier, that the carbonation is happening because of carbon dioxide penetrating the surface of the concrete and reaching the level of the reinforcing steel where the pH is brought down to suboptimal conditions. So, when we are reducing the pH to less than 11, there are some concerns about what that number exactly is. Some people say 11.5, others say 10.5, and so on and so forth. So, when you reduce the pH to less than 11, you are actually creating conditions for corrosion or depassivation. That means the stable film that is forming around the steel surface in an alkaline environment can get unstable when you have carbon dioxide penetration leading to loss in pH. Okay. But one thing you need to remember is when carbon dioxide related corrosion actually happens, you get a uniform section loss. That means you have a slow and steady loss of the steel cross section from starting from the surface inwards. Whereas when you have chloride induced corrosion, there are local spots on the steel where the chloride concentration may exceed the other spots on the steel, right. We know that chloride is not going to uniformly diffuse, it is only going to come in where there is a substantial concentration gradient, where there is an interconnected network of porosity available, and so on and so forth. And again, the nature of the reaction of chloride with the passivating layer that forms on the steel surface is such that there is a pitting type corrosion that actually happens when chlorides actually attack the concrete. Okay. So, when chlorides attack the reinforcement, it forms a local area where the cross section can be significantly reduced. So, it is called a pitting type of corrosion, and truly speaking this one is a lot more disastrous as compared to the carbonation induced corrosion, because that is more uniform. You have a slow and steady loss of cross section. Here you have a sudden loss of cross section at a single point, and you know very well that a steel rebar, if it has a localized defect, can lead to the failure of the entire system. Okay. So, the chloride induced corrosion, which leads to pitting type corrosion because of non-uniform section loss, is a lot more dangerous as compared to the carbonation induced corrosion. So, again this is carbonation induced corrosion, which we talked about the fact that carbonation or carbon dioxide penetration into the concrete is extremely severe, particularly for certain ranges of relative humidity between 60 and 70%. Okay. So, for example, structures like this compound wall, which is standing on the outside, direct exposure to the atmosphere, and again in these walls obviously the cover to the reinforcing steel will not be very much. right? It is not a major structure, so we do not really provide a large cover to the reinforcing steel, and so you start getting corrosion of the steel in such cases quite easily. And as we discussed earlier, the corrosion or the propagation of carbon dioxide diffusion into the concrete is detected by the phenolphthalein test. So, phenolphthalein is an acid base indicator. So, when the concrete is alkaline, phenolphthalein spraying on the concrete will induce a pink color. When the concrete becomes acidic, and actually when the pH becomes less than 9, the concrete will show up to be colorless when phenolphthalein is sprayed on it. Now, this is often a problem in detecting what is the critical level of carbonation that has happened in a system. If you use phenolphthalein test, the discoloration will happen only when the pH crosses the barrier of 9, but most researchers tend to believe that that is already a little bit too late. Okay? When your pH is reaching less than 11 itself, the stable passive film around the steel has already started deteriorating. So, there has to be other means to actually understand what the depth of the carbonation front is without really relying too much on the phenolphthalein test. So, today many people use what is known as a rainbow indicator. Now, as the name implies, a rainbow indicator will indicate different colors for different pH levels. Okay? So, you can actually track the actual carbonation front into the concrete by detecting minute changes in pH by a factor of 0.5, 0.5 and so on. So, you have very many different colors based upon the actual pH that is inside the concrete. Okay. Whereas, phenolphthalein wants that pH to be much less than 9 to create the colorless condition. So, indication of carbonation depth could be a critical factor in looking at concretes which are in the field and trying to understand their propensity for getting corroded. Okay, chloride induced corrosion, as I said, chlorides are propagating through the cover layer of concrete and reaching the steel surface. Again, when high chloride content is present, the passive layer gets broken down, and then once the corrosion initiates, the pits start growing in the steel. Okay, so, once corrosion initiates, the pits start forming, and when the pits form, you have a local loss of cross section that leads to a loss in structural capacity of the steel. Now, when you look at the reactions involved with this, the passive layer is actually going to be reacting with the chloride ions to lead to the formation of iron chloride. Okay? And this iron chloride may actually again get transformed into an acidic phase like hydrochloric acid, and that may lead to a further deterioration. So, actually this reaction is self sustaining. So, once the reaction of the chloride with the external film happens, it can be a self sustaining reaction that leads to more and more damage of the steel happening in the system. Okay. So, you need to be a little bit careful about how your steel, or rather you need to be very careful about how concrete in a chloride induced environment will perform, because ultimately the reaction that starts with corrosion can be a self sustaining reaction, and that will lead to more and more progressive kind of damage which will happen. So, the process is regenerating, and it does not spread all along the bar, it tends to localize and forms the pit. So, again these are examples from different kinds of steel systems. This is a 7-wire strand which is used for pre-stressing. You can clearly see the pits forming in the system, and of course, in a regular deformed bar also you can see several signs of pits forming due to corrosion of the reinforcing steel. This is a microscopic image of a uniform layer of corrosion products on the steel surface. You see here, there is a uniform layer of corrosion products on the steel surface. This is done with microscopic imaging where the binarization has been done. Concrete has been made entirely black, and steel, because of its much higher density as compared to concrete, has been made completely white. The intermediate rust products, which are having a lesser density than steel, are showing different shades of grey, and you can see here that you are forming different forms of rust. There is one darker grey rust and one lighter grey rust. So, different densities of rust are actually forming in the system, and there is a lot of cracking which indicates that there is some volumetric changes that are happening in the system. Again, this is an example of a chloride induced corrosion. You see that there is a pit locally forming in the steel, and that is leading to a greater removal of cross section from that location. So, what are the factors that influence the rate of corrosion? We have talked about this before, but just to reiterate, we need oxygen and moisture for the corrosion reaction to propagate. So, we need the oxygen moisture availability at the cathode for controlling the rate of the reaction. The resistivity of the medium is very important because your ionic transfer happens through the electrolyte, that is concrete in this case. So, if concrete is highly resistive, it will resist the transfer of ions. So, it will slow down the rate of corrosion. And of course, the passivation of steel is something we have already discussed. In the alkaline environment, you are forming this iron oxide hydroxide layer that is leading the steel to be passive in an alkaline environment. With time, as pH conditions change or when chloride penetrates the system and attacks the passive film, you start initiating the corrosion process. So, if you look at this in a schematic diagram, so you have your steel here, you have the anode which is formed inside the steel, and the ionic flow is happening through the concrete. So, the resistivity of the concrete is a critical factor. And what does resistivity of the concrete depend on? The moisture content of the concrete and interconnectivity of the pores, right, because the conductive concrete would mean that you have a saturated concrete and the pores are interconnected, which leads for a high conduction possibility in the system. If the pores are not interconnected, then your resistivity is going to be extremely high and ionic transfer will be impeded. For example, if you have a system with mineral admixtures, you can expect your resistivity to be much higher than that of regular concrete. So, in a chloride induced corrosion environment, you might actually get a very positive response when you use mineral admixtures as replacement for cement. In a carbonation environment, we discussed earlier, you have greater porosity after carbonation in the systems with supplementary cementing materials. So, you may actually end up causing a lot of these pores to get interconnected when the carbonation process happens. But the other factor, that is the availability of oxygen and moisture, may still be restricted in a system with supplementary cementing materials. So, there are a number of factors that can actually influence the rate of corrosion once the concrete is carbonated. But with chloride, you can definitely be sure that all these factors like concrete cover, the diffusion of oxygen and moisture into the system, as well as the resistivity, all these factors will be positively affected when cement is replaced by supplementary cementing materials. Now, if you look at the propagation of corrosion as to how once corrosion initiates, how does it propagate? If you look at the degree of corrosion, extent of corrosion that is happening with time, you will see that initially for a long time the steel, although it is actively undergoing the process of corrosion because of ingress of carbon dioxide or presence of chloride, steel does not really get damaged because the chloride takes some time to reach the steel surface, or the carbonation front takes some time to reach the steel surface and cause a reduction in the pH. So, that is determined by what? No, diffusion is a phenomenon leading to the penetration of chloride or carbon dioxide. But what is the primary factor that is governing that? The cover concrete, right? The extent of the depth of the cover and the quality of the cover, quality in terms of permeability of the cover, right. So, the cover being deep or the cover being less permeable would tend to increase the time it takes for depassivation to happen. So, a lot of protection strategies against corrosion are obviously based on improving the concrete cover characteristics. Now, beyond this process, we call this as the depassivation time, okay, or the initiation time. So, the concrete steel corrosion starts getting initiated at that point, and from here on the rate of damage to the steel increases. So, degree of corrosion is typically measured in terms of loss of cross section per year. So, like millimeters per year, like that, okay, that is typically the unit of degree of corrosion. So, when you look at stage 2, which is the propagation phase, right, you have a increase in the rate of damage that is happening to the steel. Now, you see that there is a transition here from stage 2 to stage 3, and you see that there is an increase in the rate of deterioration of your concrete, not concrete, of the steel, okay. Why do you see that? Because of acceleration of your damage. Why does damage acceleration happen? Because the steel rusting leads to a cracking in the concrete, and more cracking implies there is further ingress of aggressive species into the concrete, and the rate of acceleration of damage happens. So, you have initiation stage, propagation and acceleration stage. So, this is actually this was originally proposed by a scientist named Tutti. So, this is called Tutti's diagram, okay. Of course, you will not be able to make out these transitions very clearly. Mostly what you will see is a more gradual increase in the rate of the corrosion, okay. But then it's been simplified into this trilinear sort of a diagram so that you understand what are the different phases. So here the first phase is obviously governed by the depth of cover and the quality of the cover. What else can determine the length of this passivation time? What about the steel itself? Will the type of steel matter in terms of the depassivation time? Obviously it will matter, because if you have regular steel versus stainless steel, the quality of the passive film that is forming will be quite different. In stainless steel, the passive film that forms remains stable for a very long time. So because of that, the corrosion process does not get initiated itself in the stainless steel. Okay. Now once the process is initiated, when you move to the stage 2, what do you think are the factors controlling the propagation of corrosion? Oh, one more thing that I forgot here, cracking. If there is cracking of the cover concrete, obviously there will be a greater or faster initiation of the corrosion process, right. So cracking will lead to quicker ingress of your aggressive agents, and that will lead to a faster initiation of corrosion. So yeah, we were talking about the second phase. So what are the primary characteristics of the concrete that are controlling the second phase? You see, the type of steel will again be important, no doubt. The rate at which steel deteriorates could be different for different types of steel, no doubt. What else? What is happening in the second stage? The corrosion is initiated, so there is ionic flow happening in the system. So what is controlling that ionic flow? The conductivity of the medium or the resistivity of the concrete. Now this resistivity of concrete again is linked to the quality of the cover, right. Impermeability of the cover again determines the resistivity of the concrete. So the primary factor really that affects the rate of corrosion, whether initiation or propagation, is the quality of the cover concrete. And in most cases, the economically feasible solutions to prevent corrosion or to extend the period of corrosion to beyond the service life of your structure are related to improving the quality of the cover concrete. Now of course that may include several different things: reducing water cement ratio, using supplementary cementing materials in case you are using, in case you are designing against chloride induced corrosion, right. Alternatively, you could also use corrosion inhibitors, okay, which can prolong this length of the passivation time. Of course, corrosion inhibitors can act in many ways. One of the ways that they can act is by making the concrete more watertight. So that means your ingress of aggressive species will slow down, will be getting slowed down when you have corrosion inhibitors in the system, certain types of corrosion inhibitors. Okay. So all those factors can affect the kind of cover concrete that you actually have. So most critical parameter that determines the rate of corrosion of your steel is still the cover concrete quality. Now the concept of corrosion initiation and propagation can be combined into understanding the service life of a reinforced concrete structure, because most researchers tend to agree that the kind of durability mechanism that really deteriorates concrete the most or affects the service life the most is obviously the corrosion of the reinforcing steel, because that leads to a loss of structural capacity. Okay. So service life is obviously defined as the time during which the structure is able to safely meet the requirements, user requirements. Of course, this may mean different things to different people. For example, when you are defining service life or serviceability limit, for example, when you do the IS 456 based design, the serviceability limit for a slab may indicate the extent of deflection that happens in the slab or the amount of cracking that happens in the tensile zone of the slab, right, crack width for example. But here we are talking about the time taken for the initiation of corrosion as the end of the service life. Truly speaking, that is not the end of the service life, because even after corrosion initiates, there may still be some useful performance left in your building. Okay. And if you really look at it, the initiation phase is where there is no damage happening. The propagation is where the damage actually happens. If it reaches a critical level, we say that that is the end of your service life. But then if we identify that and do a repair, we can then extend the service life further. Okay. So corrosion mitigation often involves a proper management of the inspection of what is happening to your reinforced concrete, and then putting in timely repairs to ensure that you can actually further extend the service life of your building. So this is the propagation phase, and finally you have the repair phase. So actual service life is coming all the way till the end here. The problem is this part is not as easily predictable as this part here. Given the choice of your binder systems, given the water to cement ratio of your concrete, given the type of steel, there are models that you can use for fairly accurately predicting what is the end of the initiation phase? That means what is the point where the steel actually starts corroding significantly. But the problem is this next part is not that easy to model, because of which most service life models will tend to treat only the initiation phase as the end of service life. So, in most cases this is taken as the service life of your structure. Now, that is if you want to have it in a deterministic sense. If you want a probabilistic service life, that means you need to account for the fact that your structure may not be free of defects in the beginning itself. You may actually have some defects there, because of which you need to do a probabilistic analysis. So, the probabilistic service life will have a range of values of the service life. It will not be one single deterministic value of the service life. Okay. So, all that actually is captured in several service life models, which one of which we will see in just a minute. Before that, let us look at some critical service life parameters. One is the material parameters of steel and concrete. So, again we are talking about the apparent diffusion coefficient of the concrete, the critical chloride threshold value, and the corrosion rate. Okay. So, these are all the critical parameters affecting the service life. Now, we are considering corrosion rate implies that we are also looking at the propagation phase. Right. If we do not consider corrosion rate, we are only looking at the initiation phase of the reaction. Now, design parameters include cover depth, because you can always vary the cover depth to check whether your design is satisfying the requirement or not. And then the other aspect is the environmental exposure parameter. How soon does the chloride build up at the surface of the concrete? The critical or surface chloride build-up rate will depend on the kind of environment your concrete is in. For example, if your concrete is directly exposed to marine conditions, then the chloride is immediately building up in the beginning. If your concrete is sitting inside a chloride infested soil, it will take some time for the chlorides to actually build up to a large concentration on the surface of the concrete, which will lead to an increase in the level of diffusion. But this state of very high chloride concentration at the surface may take some time to actually happen. So, some of these models actually account also for the time it takes for that build up to happen. Now, looking at critical chloride threshold levels of various steels, these are stainless steels SS 304 and 316. There is a micro composite steel, and you have your regular brands of reinforcing steel. You can see the range of performance is quite different. So, this is critical chloride threshold value in pounds per cubic yard, and this is in kilogram per cubic meter. Of course, when you work in the US, you have to put both these values, because Americans will not understand anything other than this. Other world people cannot understand anything other than this. So, you need to put both these values. So, you get totally different results when you test different types of steel. So, critical chloride threshold will vary with the type of steel that you use in the concrete. Now, interestingly, when you use inhibitors, corrosion inhibitors, you can again lead to a change in the critical chloride threshold of the concrete. So, the data from literature for concrete without corrosion inhibitor seems to indicate that the chloride threshold is varying significantly. Look at the extent of variation, all the way from 0.2 to about 1.5. Okay. But generally this is percentage by weight of cement. Okay. Chloride threshold or chloride concentration is measured in terms of percentage by weight of cement. The generally accepted value is 0.4%. It is a very conservative value, because often it turns out that it is much higher than that. Okay. Now, in an experimental study done by one of our PhD students, it was found that for concretes that were tested in our lab, the average was about 1.1 without inhibitor, and for an anodic inhibitor, okay, which basically works towards suppressing the anodic reaction, that is conversion of Fe to Fe2 plus. For that type of inhibitor, it was pushed up marginally, but for a bipolar inhibitor, that means which works both on the anode and the cathode, your results were much more better. So, the actual mean was around 2. So, the inhibitors can have an influence on the chloride threshold. Now, based on these parameters, an analysis of the service life of the concrete was done using a software called Life 365, about which I will explain in just a minute. So, for this, of course, there were certain things that were assumed. One is the cover depth was assumed as 50 millimeters. This concrete was designed with a water binder ratio of 0.45, and the diffusion coefficient of the concrete was 8.87 into 10 power minus 12 square meter per second. So, based on this, what Jayachandran, who worked on this PhD thesis, was able to show was, with no inhibitor, the probabilistic service life had an average of 9.2 years. Okay. So, of course, this distribution is a probability density function of the service life. So, if you are taking 50% or the mean, It is about 9.2 years in the case of concrete without any inhibitor. When you use a calcium nitrate which is an anodic inhibitor, you extend it to almost double, 18.4 years, and for a bipolar you are taking it to more than 3 times the service life predicted without the inhibitor. Okay. So, again inhibitors can have a significant influence on the service life. Now, Life 365 for the most part takes only the initiation phase for determination of service life. It takes a little bit of propagation phase. What it does is it takes the initiation phase and adds a certain number of years for 10% damage level to happen in the steel. That means the cross sectionality of steel reduces by 10%, and that is taken to be a point where your service life is considered to be over. Okay. So, they are just adding a small quantity to indicate that 10%. So, most of the measurement is only for the initiation time, it only takes a small bit for the propagation time. Now, interestingly, when you use corrosion inhibitors, the concrete properties also seem to get affected. So, for example, here without any inhibitor, the concrete that was designed for this project had a strength between 35 and 40 megapascals. When the actual dosage of the inhibitor was used, the same strength level was achieved, but when different dosage, that means 20% and 40% below the actual or 20% and 40% above the actual were used, there was a significant difference in the compressive strength performance of the concrete. That seems to indicate that one of the parameters that you should check when you put in corrosion inhibitor in your system is also its influence on the mechanical properties of the concrete. So, Life 365 is a freely downloadable service life design software. It is not that difficult to use. There are tutorials which will help you actually determine what you need to do for different kinds of systems that you are choosing to look at. So, just to give you a snapshot of what this project, the software has, there are pages where you can actually enter the details of the kind of element that you are trying to test. For example, slabs and walls where there is one dimensional diffusion, or if you have a column, it is going to be a 2-dimensional diffusion, right. You can put the thickness of the member, the reinforcement depth or the cover depth, and the area that is exposed to the chloride. Okay. And chloride units can also be given in terms of percentage weight concentration. It gives you, of course, this is the details of the structure. You can see this is a slab with a cover thickness of 60 millimeters, and there are 2 layers of reinforcing steel here. Okay. And what you can also enter are the local environment details, for example, temperature and relative humidity for the local environment. There are preset environments created for North American cities, because this software is developed in North America. The easiest way is to find a city which closely resembles what you are trying to investigate. For example, Chennai, the closest cities in North America would be cities in Florida like Miami, for instance. You can choose a city like that and put, or you can have your own temperature and relative humidity data fed into the system. The chloride data can also be included in terms of how much chloride has been found in the seawater or the groundwater which you are designing for. You can also decide on how long it takes for the chloride to build up to its maximum level on the surface of the concrete. In a marine condition, it is immediate. Okay. In a soil, you can assume it will happen over several years, and only after that you will have the real increase in the process of diffusion. So, based on that, you can investigate the potential for different types of binder systems. So, the software allows you to test your predicted service life for different types of binder systems, because when you change the binder, what gets affected is your diffusion coefficient D28. Now, please remember D28 is a diffusion coefficient at 28 days. What the software also does is converts this into a time dependent diffusion coefficient by using a factor called M, or the decay coefficient. The meaning of decay coefficient is it is trying to track how the diffusion coefficient will decay with respect to time, because concrete gets more and more dense and impermeable, the diffusion coefficient will keep on reducing with time, right. So, here for concretes which are fly ash or slag, you can expect that your decay coefficients are much larger, 0.6 for fly ash, for slag it is around 0.5, for slag silica fume combination is about 0.3. So, the binder will affect not only the decay coefficient, but it will also affect the diffusion coefficient at 28 days, especially silica fume based binders you see are tremendously reducing the diffusion coefficient at 28 days. For all the other systems, it is assumed to not change the 28-day diffusion coefficient, okay, but because of the effect of M, this diffusion coefficient across the passage of time will change. So, because of that you start seeing that for the control concrete your average service life predicted in this environment is only 5 years, whereas the prediction of service life keeps on increasing for other binder systems that you are using in this system. So, the results are given here about 5 years, 20 years in the case of 50% fly ash, about 12 years in the case of 50% slag, combination of fly ash and slag is 15 years, and silica fume and slag combination gives you 33 years. So, there can be a massive difference. Of course, this does not mean that your concrete will behave the same way on site. This is just a means of selecting the right kind of material combinations that you have for your project. So, this is a selection criteria. It helps you to understand what kind of blend of materials you should select for the construction project without really worrying about the long term durability in the beginning itself. So, again this is some examples from water cement ratio and silica fume usage. So, for example, at 0.4 water cement ratio, just inclusion of 15% fly ash changes the initiation time by 20 years. If you have 15% silica fume, it triples the initiation time from 60 to 180 years. Of course, these are only numbers. Please remember, these may not have real life significance because the silica fume concrete will have other problems. Plastic shrinkage we discussed, that will create cracking. There is cracking, there is faster initiation. So, all that will have to be accounted for when you do the real design. Okay. So, that is why all these numbers have to be taken with a pinch of salt. This is only to do initial material selection. With 0.6 water cement ratio, from 0.4 to 0.6 when you change water cement ratio, you are losing about 20 years of service life, obviously because lower water cement ratio implies a better performance. Again here the impact on service life is not as great as the impact at lower water cement ratio. Again, for Bandra Worli Sea-Link, silica fume concrete was used with some considerations of the Life 365 based design to understand whether it would meet the demands of the long service life in an extremely aggressive environment. Of course, you know very well about different protection mechanisms against corrosion. We have been discussing those. Galvanization is a process where you cover the steel with a metal which is more electrochemically active, and you can also do a cathodic protection. Galvanization is actually one of the means of cathodic protection. Essentially, cathodic protection talks about any process that makes the steel the cathode. You prevent oxidation of the steel. Okay. So, you can supply current to it, you can cover it with a more electrochemically active material like zinc, or you can connect it with another material like magnesium for instance, which can corrode while steel remains safe. Stainless steel has a very high chromium content that makes a passivating film very stable, and that prevents further corrosion of the steel. Epoxy coated steel is very expensive. We also talked about the fact that blisters or pinholes in epoxy coated steel could actually make its performance worse than regular steel. Corrosion inhibitors can be of many types. We discussed the mechanisms earlier. Some of these can form, they can be passivators of steel, they can form film on the steel surface, they can make the paste hydrophobic or waterproof, because of which water will not be able to get in, propagation rate will be reduced. Some can be also oxygen scavengers, they can combine or bind the oxygen and prevent it from reaching the steel surface. Okay. Again, these are expensive materials, so you have to think quite carefully about how to use them, how best to utilize them. There are migrating corrosion inhibitors also available today in the market, which are spray or brush applied on the surface, and they penetrate or diffuse through the concrete to the level of the reinforcing steel and offer protection. Of course, sounds like science fiction. In some cases it may actually be science fiction. In most cases the admixtures that work better are the ones which are admixed into the concrete, which are mixed with the concrete itself. And of course, this is the simple mantra, but the one which is most difficult to execute on the site is to produce concrete which has the right depth of cover and low permeability. Very quickly I will show you a couple of cases of reinforcement corrosion which was caused because of different things. This first example deals with a damaged chimney in a captive power plant in Chhattisgarh. This is an example of a poor construction practice leading to failure. So, the chimney basically is an 85 meters tall chimney you see here at the bottom in the power plant. It is a small power plant, it is a captive power plant which only serves the cement company which is right next to it, Lafarge Cement Company. And the kind of damage that was seen, this was at the ground level. So, at around this level 1.5 meters from the ground, there are air holes which are supposed to be open to allow the passage of gases and air out into the system to push the gas up. Okay. Now, here
these air holes were blocked and there was this yellowish deposit, again strongly smelling of sulfur. The coal has very little sulfur, it is not very high sulfur, but then still the sulfur flies out with the flue gas, but then a lot of sulfur was actually detected in this, and the sulfur obviously can be detected in the form of hydrogen sulfide gas. So this is the damage which was at 15.5 meter level. Of course, that was the level to which they could erect the scaffolding. They could not really go beyond that. Otherwise, we had to take the rung ladder on the side of the chimney. I was not too excited about doing that. So there was a scaffolding at 15 meter level, which we climbed, and we saw that there was a layer where the concrete had completely got blistered. You see, the concrete has completely got blistered. The steel is very badly corroded inside. Okay, and this sort of a pattern was repeating itself across the height of the chimney. So what is the common construction method for a chimney? Slip forming. Okay, if you don't do a good job of slip forming, you create joints between the different lifts, and very clearly all this damage was actually happening at the joints. But this was only after about 2 years of construction. So what could have happened here? This gas with hydrogen sulfide was somehow finding its way through the joints, and when it was coming to the external surface, it was condensing as acid, sulfuric acid. So it is almost like acid attack. You can see the blistering of the concrete surface. And we also saw at the same level there was a location which did not show much damage, but there were signs of something initiating, and we could actually feel the gas coming out at that location, and the smell was also there, the gas was also, you could feel the heat of the gas coming out at that point. So we also took some samples of concrete from the damaged areas. You can see the pH, extremely acidic pH was determined, and we also took a sample of good concrete which had more than 11 pH in this case. So there are indications, clear indications of the acid attack, but then why does this gas tend to go through the concrete? So when you have a concrete chimney, usually they have a steel tube inside that discharges the gas out, or they have an acid brick lining which is protecting the concrete from the gases that are flying out. So here they had the acid brick lining, but please remember the acid brick lining has to be supported on corbels that come through the concrete, and those locations there are possibilities of gaps being created where the gas can actually stray out and then it starts coming out from the concrete. So that is what we detected was the cause here. The problem was the poor quality construction done with the slip forming, and that led to the failure. There is another example of an ammonium chloride building at Tamil Nadu Petrochemicals Limited in Manali, which is north of Chennai. So this was an example of a building past its service life. So this building was intended to handle ammonium chloride. You can hardly imagine something more corrosive than that. This building was built around 40 years ago at the time of inspection, which was 10 years ago. So right now it is 50 years. So 40 years ago that building was built, and for 40 years, possibly in 1960s when the building was built, the concrete grade would have been very low, 20-25 megapascal concrete. Nobody thought about all these issues there. So the first impression is the best. The columns are showing vertical cracks, so you obviously do not feel safe entering the building. The workers were complaining, rightfully so, that they were quite scared about what will happen inside the building, and of course they have also maintained it very neatly and cleanly. There is chloride all over the place, and the results are there for you to see. There is corrosion of every possible structural element that is inside this system. And one interesting part is we inspected the structure in 2008. In 1991 there was a repair done where they simply removed the cracked concrete and put a new layer of mortar. You can see the layer of mortar, and this layer has nicely debonded and come off because they have not stopped the corrosion of the steel. They have only treated the symptom, they have not really treated the cause. So by putting this new layer, again because of the expansive pressures, the layer simply came off. So, and this is an interesting problem on Old Mahabalipuram Road, where a newly built structure after about 6 to 7 years started showing some corrosion related cracking in some of the columns in the basement. Now this structure was originally intended to be a 3-story structure, ground plus 3, but during the construction process they got permission to extend it to ground plus 7. So because of that they decided, okay, they will strengthen some of the columns, okay, increase the size of some of the columns by jacketing. So about 10 columns were chosen from the basement level to about 3rd floor level to jacket, and that was considered sufficient. They also built some additional shear walls and things like that. All these jacketed columns were the ones which were showing the signs of corrosion. No other columns showed any corrosion. Very interesting. So we started investigating. Of course you can see the kinds of corrosion that is happening. extensive corrosion has actually happened, not just small amount of corrosion. We did measurements with half cell potential studies and we determined that the corrosion potentials were very high. That means that most cases all the jacketed columns seem to be showing the damage. Chloride contents only in the jacketed columns were extremely high. Okay. Now chloride content, if you look at IS 456 in reinforced concrete, you are not permitted to have more than 0.6 kilogram per cubic meter of chloride. Okay. Now that is a conservative estimate, usually at 0.6 you do not really see a problem, but then that is taken in a conservative fashion. So here you can see in some cases you have 6% chloride or 6 kilogram per cubic meter chloride. Very large chloride loading is there in the system. Where is this chloride coming from? So we tried to analyze soil, nothing is there. There is no leakage, there is no way the chloride could come. What is the answer? Either curing water or the sand that was used in the jacketing portion alone. Only for the jacketed concrete this problem was there. So this OMR not too far from the sea, so you can get sea water, you can get sea sand. God knows what they did. Ultimately it was damaged, all the jacketed columns were damaged. Okay, so I have to acknowledge Dr. Pillai for helping me with some of the notes on corrosion and Dr. Balasubramanian for getting access to some of these sites and getting to see the kind of corrosion related damage that actually happened. Okay, so thanks. With that we finish this corrosion chapter. Tomorrow, the last class of the course, we will take up the issue of alkali silica reaction and freezing and thawing, and with that the theory part will be completed. Thank you.